this is a joint work with Delia Ischiera, that's working on Sapienza Università di Roma, Gabriele Nornberg from Universidade de Chile, and Hugo Tavares from Universidade de Lisboa. So basically, I'm going to talk about this paper here. And so if we scan this code here, we are going to access the PDF from arXiv. And okay, so the motivation to the problem that we investigated here is to understand the phenomena of principal eigenvalues. Here we have two eigenvalues and eigenfunctions for in the context of systems, and maximum principle and solvability, the relation between maximum principle and solvability for these systems. And we have been working also, the motivation is linked to some problems that we have worked on, UV type problems for systems, and symmetry results, and also the structural nodal sets for nodal solutions of Hamiltonian systems. But essentially, the message today is linked to these two topics here. And as I said, when talking about Hamiltonian system, I've been working on this since my PhD, and Di Jairo is the one that have been working for a long time and may have major contributions for Hamiltonian systems. And just to mention that a very simple question, and has been conjecture, I would say long-standing conjecture, is the so-called lane-Emden conjecture for the Hamiltonian systems, that claims the non-existence of positive solutions for these systems in the subcritical. Subcritical means when I have strict inequality here, and subcritical and superlinear regime. So this is, I would say, that one of the main, or maybe the main open questions for Hamiltonian system is this, the lane-Emden conjecture. So we have been working on this, but so far the problem is difficult to solve. And okay, but I would say that linked to this major question here, we have done some related results, and today I'm going to talk about simple questions about eigenvalues. So the outline of my talk, I'm going to start with the linear scalar case. Then in the linear scalar case, when we have a self-adjoint second order operator, we know that the first eigenvalue of the operator, so the problem I would say is variational. We have the variational characterization for the first eigenvalue of this kind of second order operator. When we still in the context of linear operator, but in the non-self-adjoint framework, so the first eigenvalue is defined as the sub of lambda, such that there is a positive super solution for the problem, linear problem with lambda. So this is how we define first eigenvalue for non-self-adjoint operator. When we go to the fully nonlinear scenario. So the definition change, so this is just extensions. So to reach the nonlinear, for nonlinear operators. So the first eigenvalue problem is this one. So, and then we have what we call the half eigenvalues. We are going to have two eigenvalues here. So the which you call lambda 1 plus and lambda 1 minus. And lambda 1 plus associated the nonlinear operator in the weighted case, okay, is the sum of lambda such that phi plus lambda is non-empty, where phi plus lambda is the set of functions phi, positive functions, which are super solutions for the problem. And lambda 1 minus is in the set, is defined using this set here, again, sub, with of negative functions that are sub-solutions. And so this was investigated by Sirakov and Quaz, and they proved that, and they have shown that cases in the nonlinear, I'm searching. In the nonlinear case operators, we have the existence of two different first eigenvalues, okay? So this is, you say, signed. So here, observe that for these eigenvalues, here we have signed eigenfunctions, okay? And just to show that this phenomenon appear very naturally, let us consider the very basic, I would say, linear operator and this nonlinear problem here, and which is called Fouchique, kind of Fouchique problem. So if you just to simplify things, consider L equals to the Laplacian operator. And suppose that U is a solution of this Fouchique problem here. We like it. For me and maybe many of you, so the L will be the Laplacian, so minus L is the minus Laplacian, where maybe many of you prefer, as I do. But, okay, so we put this on this side, and we have the minus Laplacian of U equals to this, okay? And for, here, as I said, we can consider the Laplacian, and kappa is a positive number. Then we can construct very simple nonlinear operator. For example, if we consider F1 equals the maximum of L of U and kappa times L of U. So this is a nonlinear operator. And if U solves this problem, then U is an eigenfunction of this operator here. And also U turns to be an eigenfunction in the case kappa, when kappa is greater or equals to 1. This is simple calculations, believe me, just definition of maximum, and consider the positive part and negative part of the function. Just to make clear that U minus here is minus the minimum of 0 and u. Okay? So this means that u minus is always greater or equals to 0. Okay? And u is equals to u plus minus u minus. Okay? In F2, if you consider this, and in the case that kappa is less or equals to 1, then we have that u is also an eigenfunction associated to F2. So this means that we can read the Fuchs type problem as an eigenvalue of a nonlinear operator. And again, the gyro is going to appear many times here in my talk, and the gyro and Jean-Pierre, we have very, let's say, they will have interesting results for the Fuchs spectrum. And so they, I would say, the basic contributions are there in this paper here. And what I want to stress here is, if we consider the case where L is the Laplacian, kappa is bigger than 1, then we see in this example here that the lambda 1 plus of F1 is the first eigenvalue of the Laplacian, and the lambda 1 minus of the same operator, F1, is kappa times lambda 1 omega, where lambda 1 omega is the first eigenvalue of the Laplacian. So we see, so if you consider this simple example here, so we have that the two half eigenvalues are different. So this is just to understand this phenomena for very basic nonlinear operator. So we have two different, and of course here, and if you, which are, so we have the positive, suppose that lambda 1 is a positive eigenfunction of the Laplacian, okay? Oops. Lambda 1 phi 1, then associated to this, I'm sorry, associated to the lambda 1 plus, we have phi 1. This is associated to this half eigenvalue, and minus phi 1 is associated to this half eigenvalue. So just to have in mind that for the scalar case, simple nonlinear operator, we have that these two different eigenvalues associated to signed eigenfunctions. So lambda 1 plus is associated to positive eigenfunctions, lambda 1 minus associated to negative eigenfunctions. And I mean, the subject of my talk is very simple, as you see here, is eigenvalues and eigenfunctions. So basic questions for operators, elliptic operators. And there are many contributions. And for example, the work of Di Jairo and Gosset for the monotonicity of eigenvalues with respect to weights, because here we have weights in our equations, and also unique continuation principles, and the very important paper of Berestik, Nirenberg, Varadin, where the characterizations of eigenvalues via the maximum principle, Busca, Esteban, and Quas, the radial eigenvalues for Pucci operator when we go to the context of fully nonlinear operators. Ishii and Yoshimura for the Isaacs operators, Quasi and Sirachov for convex operators and half eigenvalues, okay? And Armstrong for non-convex operators, also for including the second eigenvalue. E comma E she for radial eigenfunctions for fully nonlinear operators. Felmer E comma for eigenvalues of the one-dimensional Puch operator with potentials. And Gabrieli Norberg for eigenvalues for proper operators and so on. So this is just to mention some related works. And for the operators that we consider in this work, we saw the very basic ones when we take maximum and minimum or between Laplacian and the constant times Laplacian. And if you want to restrict yourself to that case, okay, we have an example of a nonlinear operator. But here, in general, the hypothesis that we assume here is this structure hypothesis, which we call H1, okay? And here the operator L plus, he involves the M plus the Puch plus operator times this, the part that involves the gradient, and here the zero orth term, okay? And the hypothesis that, just to emphasize that here we consider unbounded coefficients, possibly unbounded coefficients, just on the lines of the contributions of Gabrieli for the work she did for the PhD thesis. So gamma, rho bigger than n, and the weights gamma and theta are non-negative, and theta is, gamma can be zero, identically zero, but rho, we assume that it's non-zero, okay? Non-negative, but non-zero everywhere. And I'm sorry. And for some alpha and beta, the Puch operator that appears here are defined, just to recall, are defined by this, okay? And for me, and those that are more familiar with linear operator, just think that the Puch operator is a very natural extension of the Laplacian, because when alpha equals beta equals 1, m plus and m minus, they coincide with the Laplacian operator, okay? Okay, so Puch operator, again, you may see is a very natural extension of the Laplacian operator. We consider these extremal operators, which we call F star and F sub star here, is defined here. And if F satisfies H1, then F star and F sub star also satisfies H1. F star is always convex, and F sub star is a concave operator. Moreover, F coincides with F star if and only if F is convex, and F coincides with F sub star if and only if F is concave. And also, this identity holds, and for our proposed, we, in order to get some results from more standard operator and also concave and convex operators, we have these relations here that are very useful for the technical part. And we also, since we're talking about eigenvalues, it's very natural to ask the one degree of homogeneity. So we assume this condition here. And also we ask an oscillation control that's a bit technical, but this is just to have to obtain that the F star operator to prove regularity results for the solutions of the F star operator. Okay, so for example, if F satisfies this condition here, so the oscillation, X oscillation hypothesis is satisfied, okay? And we assume that F enjoys the W2 whole regularity, okay? So this is basic hypothesis. And once, if we assume this and this, we have that F star also satisfies enjoys the W2 whole regularity. So let me show to mention first some the history of eigenvalues for the systems. If we consider the case, I'm going again, when I say P and Q, please recall the powers that appears for the lane-Emden system, okay? When we have the P equals 1, P equals Q equals 1, our results are linked to this this paper by Birindelli, Mittier, and Sweers. And in the case, for the general case, when talking about eigenvalues for lane-Emden systems, this is the hypothesis that correspond to linear or one homogeneous, that makes the problem one homogeneous, and then we can talk about eigenvalues, okay? So for this general hypothesis, but in the context of linear operators, Montenegro, long time ago, this is Marcus Montenegro, long time ago, published a very interesting problem, and then he investigated the spectral curves. Just to mention, when we have the scalar problem, we have eigenvalues. For systems, the concept of eigenvalues becomes spectral curve, okay? And so I'm going to show to you how this phenomenon appears, okay? And recently, again, Marcus Montenegro and Leite, was a PhD of Marcus. They investigate the first eigenvalue and they understood the link between first eigencurve and the maximum principle and also the comparison principle. But this is again for linear operators, okay? And what we do here, so essentially we continue the work done by these people here, and we extend for the context of nonlinear operators. And as I said, we have many, the Puch operator, that operator linked to Fuchik problem. So we have very simple examples of nonlinear operators and important examples. And then we go further. I mean, we cover all these results here for the nonlinear context. Okay, so this is so we have a nonlinear operator here, and so this is a system, okay? And in the first equation, we may have different nonlinear operators within the system. It may be weighted, but I stress that the weights here are positive, okay? And not positive, non-negative. I'm going to show to you the precise hypothesis. And the Hamiltonian structure here is because, you see, we have the operator calculated on U, and we have the equation here, the nonlinear part associated to V. In the second equation, the operator, the second order operator is calculated on V, and the nonlinear part is calculated on U. So this is Hamiltonian type systems. Okay, and we have here is the lambda and mu is going to be will belong to what we call here lambda 1, lambda minus curve. The two first eigen curves, okay? But we always have, for this curve, as we see next, we have a particular when lambda equals to mu. We can reduce the problem when lambda equals to mu. This because we have the one homogeneity hypothesis on the operators, and because also we are always assuming that P times Q equals 1. Okay, and then we define lambda 1 plus, and after we'll define lambda 1 minus. So but just consider lambda 1 plus of the two operators F1 and F2 with weights tau 1 and tau 2. Just to mention to you that here we have fully nonlinear operators, but even if we consider linear operators, we include cases with different operators. Okay, so this is very, even for linear case, well, the operator or the problem is not non-variational, if you want to keep this in mind. Okay, even for linear operators, we are in possibly non-variational setting. Okay, so lambda 1 plus is the supremum of lambda such that psi lambda plus is non-empty. And how we define psi lambda plus is the set of pairs lambda phi psi with positive functions such that we see positive phi and psi are positive, and phi is a super solution here, and psi is a super solution here. Again, I always like to see this, for example, this equation, I prefer and to have when we have F1 equals to the Laplacian. So F1 of phi is greater or equals to lambda and the rest here. Okay, so we have super solution. So here, so associated to lambda 1 plus, we have positive super solutions. In lambda 1 minus, we have negative subsolutions. Okay, so this is how we define lambda 1 plus and lambda 1 minus. And these will originate, as I said, we are going to construct curves, but these curves have particular points when we are, so these curves will lie here, it will be like this, but we have a special point on the curve. This is, okay, that is in the, I would say this is lambda, and this is mu, and this is the line lambda equals to mu. So we always have this special point, and with this special point, we construct the whole curve. Okay. Okay. So once it's defined, and here just to, because again, when you go inside the technical part, we always the arguments are based, as we know, for those that have worked on systems, we very frequently we use results for the scala, in the scala. Excuse me, can you hear me?
Now we can, Professor.
Okay, okay. Okay, so lambda 1 plus, if lambda 1 plus of fi associated the weight theta is positive for both I equals 1 and 2, then lambda 1 of f1 and f2 here with theta equals 0, this is just potential, is greater or equals to 0. And this, to see this, just to consider phi 1 and psi 1 plus to see this. Okay. This is just for the technical part and also for the hypothesis that we impose. Okay, so this is just to show you that we have a kind of scaling for the system, to show you that in the general case, because the general problem we have lambda and mu here, but we can reduce where lambda equals to mu. So we have lambda 0 and lambda 0 here. So if u0 and v0 solve this, and if you give me lambda positive, and you set u equals to u0, and v equals to this scaling here of v0, and if you set mu equals to this number here, so you solve this problem. So is to show you how we construct the spectral curve, and indeed, as you see, this is the spectral curve is more or less a hyperbola. It's a hyperbola when Q equals to 1. P again, Q is 1 over P. If P equals to 1, we also have Q equals to 1. So here it's linear, okay? And in the case where it's linear, we have a hyperbola. But in general case, it's not a hyperbola, but it behaves like a hyperbola, okay? This is goes to 0. This is asymptotically goes here, okay? Then we have this. So here I show you that we can restrict the problem to when lambda equals to mu. Here, of course, I'm going in one direction, but the other directions are a bit trickier, but it also holds. So it's equivalent to consider this case. And so we see that we have a curve associated to lambda 0, okay, when we use this function here, okay? Great. So here is just to recall again the hypothesis that we call, so the structure hypothesis, homogeneity and oscillation control. This is linked to regularity, to have regularity results. And here, as I said, the remark before we assume this, because when we reduce the analysis to scalar equation, so we assume that lambda 1 plus of f star of theta is positive, okay? and F and F star satisfies this hypothesis here, okay? And F enjoy the W2 regularity when, as I said before, when F and F star satisfies this, and F enjoys the W2 regularity, the W2 regularity also holds for the F star operator. Okay, and so this is the fully nonlinear system of Hamiltonian type that we investigate. The weight here that appears here are non-negative, and we assume that they support, they intersect, okay? They have positive measure. The intersection of the support of tau1 and tau2 have positive measure. And so let omega, regular domain, assume the homogeneity condition on the structure of the P and Q here, and tau1 and tau2 satisfies this. F1 and F2 satisfy H1 to H4. Then there exist two spectral curves. So these are the spectral curves in the first quadrant corresponding to, so the first, the lambda 1 plus curve are associated to positive eigen functions, and the lambda 1 minus curve is associated to negative eigen functions. Moreover, this is now a property linked to the structure of the Hamiltonian structure that we must be careful that even for the Laplacian operators, when P is different from Q, the eigenfunctions are not is not a linear space, okay? If you consider pair, okay? It's not a linear one-dimensional space, but it's a simple curve. In this sense, any other eigenfunction associated to the curves satisfies U plus is T times V plus, and the corresponding V plus is T to the P psi plus. So the positive eigenfunctions are these, are precisely given. So it's again a curve, okay? So it's not a T to the P, okay? So it's not linear because I have one T to the power 1 here, and here I have T to the power 2. And moreover, if U and V is a signed solution, a signed eigenfunction, necessarily the pair lambda mu belongs to either lambda 1 plus or lambda 1 minus. Okay. And okay, again, we have the second result is what we call, so we have two curves, okay? So far of course, I haven't proved yet that these curves are different, but I'm going to show you that they can be different. We like to have, this is lambda 1 minus, and this is going to be lambda 1 plus. So suppose the hypothesis before, okay? So if lambda mu is an eigenvalue of the lane-Emden system, in the region, okay, I'm sorry. Okay, suppose the hypothesis before, then there exists a curve that we call sigma. Okay, so this is the curve. Then in this curve is strictly, so the curve sigma, just to put the curve here. So the curve is going to be above the two curves. So this is the curve sigma. And this curve can be parameterized again, okay? And so this is the shape of the curve. Such that if lambda mu is an eigenvalue of the lane-Emden system in the region below, if the lambda mu is below the sigma curve, so necessarily it has to be in one of the curves, okay? So then necessarily lambda mu belongs to one of the curves. In other words, in the first quadrant, below and slightly above the two curves, there are no other eigenvalues. So this is what when we for the scalar problem, when we prove that the first eigenvalue is isolated. So the first eigencurves are isolated. So we are okay. Again, let's going to shift to basic example. So let's going to turn to the Foucault-like spectrum in the context of lane-Emden systems. So as before, take F1 as this maximum. Kappa is going to be bigger than 1. Is exactly as before, okay? And F2 the minimum. And here, if you consider L is the Laplacian operator. So, as I said, Montenegro has worked for the eigenfunctions for linear operators. So, suppose from Montenegro there exists sigma and a pair of eigenfunctions, such that a first eigenfunction. Okay, so this is the first eigencurve of Montenegro. So fix this eigenvalue here, okay, in the eigenfunctions. Then the pair, if we consider phi1 plus equals to phi, phi1 plus equals to phi, and psi1 plus, okay, a multiple of psi, and if we make calculations here, okay, these calculations that I'm going to skip because I'm running out of time. And if we consider the scalar t equals to this number, we construct the lambda 1 plus associated to the lane-Emden system. It's given by this number here, okay? And again, here I'm going to skip, and the lambda 1 minus associated to the lane-Emden system with the two different operators, F1 and F2, is this number here. So we see when k is different from 1, we have construct these numbers are different. And as I said before, the eigencurves behave like this. So if these numbers here with lambda equals to mu are different, the curves are different. So here, just to show that we have different curves, but here we considered different operators, but we can also do with the same operators, for example. So if we consider F1 and F2 in the two lines of the system, so lambda 1 plus is going to be sigma, the eigenvalue from Montenegro, and this is smaller than kappa. Kappa for us is bigger than 1. This is smaller than lambda 1 minus, okay? And since these are different, again, we have different curves, okay? And here we are assuming q times q bigger than 1. But this, to show that with different operators, we construct different curves, and also with the same operators, we have different curves, okay? So this is in order to give examples of our results. And again, we link our results to the maximum minimum type of maximum minimum principle, like the work of Varadhan, Beresik, and Ehrenberg. We say that the maximum principle holds maximum principle, so capital M holds for the lane-Emden system if any viscosity subsolution of the system, okay, that means any solution pair of this inequality here. So again, I like to put, I prefer to put the minus F1 to the side, and we have subsolution. So any subsolution that's less or equals to 0 on the boundary necessarily is less or equal to 0 in the boundary. So the maximum, okay, if we put U and V, so if we control, the value on the boundary, and it satisfies this inequality here, so we control the sign everywhere in the domain. So this is the maximum. And the minimum principle, we say that when we have when we have super solutions of the problem that are non-negative on the boundary, so necessarily they are non-negative everywhere in the domain. So this is the minimum principle. And then we have this theorem where we link the maximum and minimum curve, the maximum and minimum principle, to the curves lambda 1 plus and lambda 1 minus. So suppose that all the hypotheses before, and consider the eigencurves lambda 1 plus and lambda 1 minus. Then the set lambda 1, okay, I have the curve here, lambda 1, if you put plus. So the part, the set C1 plus, okay, this set here, the closure of C1 plus is the points that are below or over on this curve here. So if lambda and mu are in this region, the first quadrant strictly below the lambda 1 plus curve, if and only if the maximum principle holds for the lane-Emden system. So this is more, again, motivated by the scalar problem. And when it are below the lambda 1 minus curve, if and only if the minimum principle holds, okay? So this is kind of, again, natural extensions for the systems, for the corresponding problems for the scalar, the equation, okay? And also here we link also our curves to the solvability of the Dirichlet problem. So if we put F1 and F2 here, so far we have 0 here. Okay, we are in the homogeneous. We are talking about the eigenvalues. So now let's go to solve the Dirichlet problem. Put F1 and F2 here. Okay, F1 and F2 in L0. If lambda and mu are in the intersection of, are below the two curves, then the Dirichlet problem is solvable among viscosity solutions. You see, when we are below the two eigencurves, principal eigencurves, we can solve this problem. Okay, so think about it when you are below, in the scalar, for the Laplacian case, in one equation, when the parameter is below the first eigenvalue, then we can solve the problem minus Laplacian of u equals to lambda u plus f. If lambda is below lambda 1, then we can solve this for every f. So this is what says the first here. But here we have to ask below the two curves. But in the case that when we talk about signed F1 and F2, and so this again enters the lambda 1 and lambda 2 curves. So if F1 and F2 are less or equal to 0, and lambda and mu is below, strictly below the lambda1 curve. It means it in the first quadrant, it's also included this vertical line chain, okay? Then the Dirichlet has a unique non-negative solution, okay? So the data are non-negative, we have non-negative solution. And F1 and F2 is greater or equals to 0, then we have that lambda mu, and lambda mu is below the lambda 1 minus curve, then the Dirichlet has a non-positive solution. Okay. Here, what we like again, when we that work on the Laplacian, look, if I put F1 to this side, for the we that like to work on linear operators. So observe that if I ask F1 negative, here I have in this concept, in writing this in that way, here we are going to have minus, okay? The minus function here, because we have to put this on that side, okay? This is F1 negative, so minus F1 is positive. And this what the reason that we have no negative solution. I'm sorry, I'm out of time, but here I think I gave to you the most important ideas of the paper. And we also have some results on anti-maximum principle. This is again motivated by work of Jean-Pierre Gosset and David Giro. And we also construct a second. We have two eigencurves, but linked to signed eigen functions. We also construct a second spectral curve linked to sign changing eigenfunction, okay? But this is, and then we also can use our results to treat the case where the powers here are superlinear. Superlinear means p times q less than 1. Then we can solve this problem here for every F1 and F2 and every lambda nu, okay? So there are some open problems. We, again, if we, there is a lecture notes of the Giro for weighted problems and sign when the weights are assigned. So we have a sequence of eigenvalues that goes to plus infinity and minus infinity. So, for example, one could investigate this kind of problem. The spectral curves of higher order. Okay, we construct a second, but there are, we expect to have infinitely many spectral curves. And something that are very important questions are about the symmetry in nodal sets. The nodal sets of sign changing eigenfunctions. So this is very important questions that I would say, and difficult questions to understand for systems. Okay. Thank you for your attention.